Forces and equilibrium. So first of all, what's a force, everybody? You probably read it. A push or a pull. Does anybody not understand that? If you can't, I will demonstrate. Anybody need a demonstration? Okay, looks like we're good. So it's a push or a pull. Good. So let's maybe give some examples of forces so that we have a better understanding of what a force is. So examples of forces. Somebody give me one. Gravity. The gravitational force is definitely an example. Good. Force due to gravity. I'm not going to call it gravity, but I'm going to call it force due to gravity or force of gravity. Because gravity is a phenomenon, right? Yeah. It's okay, we see that it happens. There's a force involved. What else is there involved with gravity? What happens when you apply a force? Anybody know? Oh, it changes the state of motion? It could. We'll get there. It accelerates, right? You guys learned that word before? What does it mean to accelerate? Go faster or go slower. Can I apply a force to make something slow down? Yeah. Put my brakes on, right? On the car. Is that a force? Yeah, we have to push with our legs. Okay. Force of gravity. What's another name for force of gravity? That's another way to say it, but what's another name for it? When we measure it often. Our weight. And the symbol we're going to use, and you write this down because this is the format that we're going to use to name different forces. It's a force, so we're going to call it capital F. Not lowercase f, but capital F. And we're going to give it subscripts to differentiate between different types of forces. What should we use to recognize force of gravity? G. Sub G. So it's a lower. You guys know what subscript is? Okay. All right. What is another force? Does anybody know of another force? Tension. Good. So we got tension force. And what's tension? Yeah, it's just a stretching force or a pulling force, right? Pulling / stretching force. What symbol should we use for tension force? That's what the book uses. So what should we use? Do you get that? It's the same format as this one. Same. Why don't I use capital T like the book does? We're going to use big T for something else. And I don't want to get it confused. Are you with me? That's the only reason why. So this is why we're choosing to use this format. Capital F to represent a force and subscript whatever type of force it is. That good? Easy enough? Okay. And just know that that's one variable. It's not two, right? When we was talking about relationships between variables, we saw that. What is that? How come? And we had a question there. Are we good with that? Okay. Does anybody know of another force that you read about? No? Friction force. Great. Friction is a force. Does anybody know what friction is? A force. Sorry. Yeah, like when we rub our hands together, what happens? They heat up because there's friction between our... Is there friction somewhere else in life? No, that's about it. It's everywhere. Everywhere. Okay? We can't live without it. That'd be kind of an interesting question. Maybe we'll talk about it when we get there. How would life be without friction? That's the thing. That's a thinking question. We're not going to get there today. Okay, so what's a good definition for friction? When you rub, there's friction? Okay, well, there is. So let's see. Is there friction when I'm rolling on this wheelchair? How do you know? Oh, I'm slowing down, right? You all see that? There's a force that causes it to slow down, but that's acceleration in the backwards direction. Okay, so let's see. And if I slide this pen, is there friction? Yeah, because it slowed down and stopped. Okay. If I am falling through the air, is there friction? Yeah. And what's the air causing us to do? Slow down. Is that friction? Yeah. Have you ever seen like a space movie where they had like a spaceship coming back to the Earth, like back in the old days? They had a little pod that they come down and you have to put a parachute on. Did you see what happened to that little pod? It heated up, right? And it was on fire because it was so hot. There's a lot of friction going through the atmosphere. Okay? So what's the direction of friction? I'm hearing a lot of stuff. Let me see a hand so I can get one solid answer and understand what you're talking about. What direction is friction always, Mary? In the opposite direction, the way the object is moving or is trying to move, right? Okay. So let's say this is a force causing slowing down, right? A force always opposing. What does opposing mean? In opposite direction, right? Opposing the direction of motion. The direction of motion or intended motion, right? Good. My last class didn't come up with that. I'm probably because this class is bigger and we have more thinkers. Because someone says something, oh yeah, okay, now I'm understanding what he means by what kind of force. What do you mean, what kind of force? It's a push or a pull, right? Any other types of forces that you can think of or that you read about? Velocity is not a force, but good thinking. Hannah. Pressure is always present when there is a force. That's kind of like saying, hey, what's another force? We talked about weight, force of gravity. What about mass? Is that a force? Is mass a force? It's not. Are mass and force, are weight and mass the same thing? No, they are not. And I bet you one of you guys are still going to say that they're the same. Next chapter, we're going to talk about them and get into the depth or the details of it. But yeah, so saying pressure and force is the same thing, that's like saying mass and weight's the same. They're directly related. If we apply a force, we're going to feel a pressure, right? If we apply more force, what's going to happen to that pressure? It goes up. What's the relationship between force and pressure? We talked about this, right? Directly related. Directly proportional. Are we good? Okay, so not quite a force, but it's related. Anything else? We don't have to. No, I just want to know. Do you know of any other forces? Oh, I'm so glad you said that. That is a common misconception. No. Is it okay to have a misconception? It sure is, and we will in this class, always. But inertia is not a force. What's inertia, right? We'll get there in chapter 3, which is next chapter. Okay? So, not quite, but great. Let's think about, okay, you guys are sitting in your chairs, right? What's the net force on you right now? Who can tell me? Raise your hand. Go ahead, Ethan. What? No, I'm asking, what is the value of the net force on you right now? Right now. 0? What do you guys think? Is it 0? Oh, hold on. The net force means what again? The sum of all the forces. So let's add all the forces. In order to do that, we have to recognize what forces are on us, right? Okay, let's see. So we say we have. So you guys want to see my art? Who do you want me to draw? Oh, Ethan. I could draw him. So I'm going to draw Ethan. Ready? Here we go. And if I were to draw Celsius, that would look the same way, right? You guys get no? Okay. So what if I draw an elephant? What's he going to look like? It's a dot. Isn't that nice? It's just easy way to draw objects in this class. Isn't that nice? So I'm just teaching you how to make things simple. You guys like simple, right?
Yeah.
Okay, good. Okay, so what forces are acting on Ethan? Someone raise your hand and tell me one force. Let's go with Caleb.
Sure.
What?
Sure.
Share?
The chair.
Oh, the chair. The chair is an object. And every time there's another object, there will be a force. That's good. That's good. So what is the force acting on Ethan? Go ahead, Tori. Force of gravity. Can you tell me the direction of gravity? Force of gravity? Straight down toward the center of the earth. You with me? So that's the center of Ethan, and it goes toward the center of the earth. Isn't that cool? How do I draw the earth? Oh, not nice? Oh, not a little bit bigger. Oh, there we go. Okay, are we good? So we have the force of gravity straight down toward the center of the earth, and we'll just label that FG. And so if you guys do the same thing, then you'll have this in your notes, and you can know how to draw force diagrams. Right? You have practice right now, and we'll get into a little bit more depth in chapter 6, but okay, we'll get there, which is right after chapter 4. No, it's after 4. 4 or 6, see? Okay, well, we're not going to do chapter 4 in this class until the very end of the year, if we get there. Or semester, anyway. I can't remember. I think year. Okay. All right, what other forces are acting on Ethan? Someone said the chair. That's not a force, that's an object. Is Ethan trying to move? Oh, he is. He's trying to move down, right? So it's kind of like friction, but we don't call that one friction. The chair is doing what to Ethan? Supporting him, isn't it? It's supporting him. So we call this a support force. Now there's a lot of different kind of support forces, so we're going to give this a special name. And I want you to know this name. A support force is a force, but there's several different types of support force. So the special name is, and in fact, I'll just write it right here. Normal force. Did you read about that force? Okay, so what the heck is the normal force? That means it's ordinary force? It's not, or it's just regular? Is that what it's, what does normal mean in math? Does anybody know? Raise your hand if you can tell me. What does normal mean in math?
Irregular.
No, that's what it means in life. What does it mean in math?
Normal.
Or normal means not irregular, right? Okay. What? Not quite. It means this is a support force, but what normal means is 90 degrees, right angle, or perpendicular. All those things mean the same thing, yeah?
Yeah.
And normal is just another one of those synonymous words. Are we good?
Yeah. Yep.
Okay, so a good definition for normal force is a support force that is always, that means it's never not, right? Always perpendicular. I'm going to write this little symbol here. You guys okay with that symbol? in the math symbol in geometry? Perpendicular to the surface that the object is on. So the object has to be on a surface in order to have a support or a normal force. Good? And is it always straight up? No, it's always perpendicular to the object that it's on, or the surface that it's on. So I have this iPad right here. Does the iPad have a normal force? What direction is it? The gravity's straight down. The force of gravity, its weight is straight down, but the support force, the normal force is straight up in this case. Why? Because the table is straight horizontal, and it has to be perpendicular to that. You with me? What if I did this? Now what direction is it? It's not straight up anymore, but it's still perpendicular to the table. Are you with me?
Yeah.
That's a good test question. What is a normal force? Great test question. Okay, so if I were you, I would write that down and star it, circle it, highlight it, whatever you got to do, right? All right, so if I'm going to draw this, here's Ethan. We have the force of gravity, and how big is my normal force going to be compared to my force of gravity? Equal. How do we know it's equal, Landon? Because he's not moving. That's good. That's one way to tell. He's not moving, so he's in a state of equilibrium. He's in a state of equilibrium. That means the net force, we know the net force is 0. We already said that before we did this, right? Yeah. So for that to be 0, well, if we pluff them, then isn't that going to make it be twice as big? How does that go to 0? Yeah, go ahead, Mary. Oh, one's going up and one's going down? How do we write opposite in math? Oh, negative. Now you guys know why we do negatives. For physics. If I'm going this way, then call that direction positive. If I'm going this way, that direction is negative. Are we good? That's how we do it mathematically. So that's a positive, that's a negative. We add them together. If they're the same amount, then they cancel. Jeremiah.
Can you explain how the normal force is perpendicular?
The definition of the word normal means perpendicular. So how is it? I don't know if I can. It just is. Now that seems like a cop-out explanation, right? But by definition, it is. How do I know? Well, let's see. Is there as much weight on that table than there is right here? There's less weight on the table, and if I push it up higher and higher and higher, what's going to happen? It's going to slide off. And there's going to be a lot less weight pushing on the table. Therefore, a lot less force pushing up. But to answer that question completely, wait till chapter 7. Oh, we always got to wait till another chapter. Yeah. But science builds on itself, right, Caleb? Science builds on itself, so we got to make sure we understand this stuff all the way before we move on. That means we got to study. Are you guys going to study between now and 24 hours? I hope so. Okay. Great question, but we'll completely answer that question in chapter 7. Sound good? If you want to read ahead, go for it. Any other questions before we move on? Okay, that was a great discussion, I hope. Did we get anything from it? All right, let's talk about vector quantities versus scalar quantities. Can anybody tell me what a vector quantity is? Oh, you guys seen this show, right?
Yeah.
Okay. So his name is what? No, that's his nerd name. But his name is Victor, and that's why I have that. You guys know Linda Matthews, Linda White?
Yeah.
She drew, let me just tell you, when she was your age, she was in this class, right? And she drew this, and it was so good. I mean, she didn't draw that. That was later. Wait for it. So she drew this on a poster, and it looked almost kind of like that, but not near as good. She was in 10th grade, and she got skilled as time went on, right? So she drew this for me, and I thought, that is great. I want that on my wall. So I put it on my wall, and everybody saw that poster. And then 2 summers ago, she called me up and says, can I redo that for you? Why? Because she got better. And there it is. Isn't that cool? I said, are you sure you painted that, or did you just buy that? You just bought that, right? Isn't that great? Oh, I love it. But one thing she did miss, compared to the first one, there's one little word there that's missing. Does anybody know? Booyah. Right? You guys ever see this show? Yeah, but I didn't remember that part because that's stupid, right? But now it's like, now I want to watch that so I can see it. It's going to be so cool. Is that how you guys are thinking? No. All right. So he goes, my nerd name is Vector because both magnitude and direction, right? And then he said, booyah, because that's cool. Isn't that cool? No, that's nerdy. All right. So a vector, so what's a quantity? What is that? Amount, right? Like a number amount, yeah? So it's a quantity. So a vector quantity is a quantity that measures both magnitude and direction. So what is magnitude? Non-magnetic sounds like it, right? But yeah, what is magnitude? What did you say? It could be the mass. No, it's not, because mass is not a vector quantity. But we're getting the right idea, maybe. The size or the amount. So we say a quantity, and we said it was the amount, right? That's basically the magnitude. The size or it could be how big, how small, how fast, how slow, how hot, how cold. The amount, how much. Okay, so that's what magnitude means. Maybe write that down. Magnitude is how much. And we all know what direction is, right?
Yeah.
It's when you get help from Heavenly Father. That's also direction. He gives you a direction to go, right? Maybe not literal, but okay, whatever. So, but direction we talk about in physics is north, south, east, west, up, down, left, right, side to side, right? Are we good? So what is a scalar quantity? Who can tell me that?
Quantity.
That measures
Magnitude, or direction.
only magnitude. That's right. So it's basically the same thing, but what? Measures only magnitude. You guys okay with those quotation marks? Or the ditto marks? What? Oh, you guys don't know what ditto marks are? You guys ever seen Ghost? Oh, you guys have homework. You ever seen Ghost? Yeah. And the girl in the show says, "I love you," and what does he say? Ditto. It means same, right? But what this? It just means it's the same. So instead of rewriting all of that, I just put ditto marks, right? Same. You never seen that? I learned you guys. I taught you guys something else that's not even physics today. Cool. All right. Are we good with scalars and vector quantities? Okay, I'm gonna draw a picture of a. We'll do that in a minute. Let's give some examples of a vector versus a scalar quantity. Can anybody start it off? I know this is the hardest part. Think, oh, what do you mean? What? Scalar or vector quantities? We talked about a couple of them today. Can anybody tell me a quantity that is a vector or a scalar quantity? Go ahead, Jeremiah. Light?
Yeah,
Lightweight. So you're talking about weight.
waves.
Oh, waves, like waves. Okay. The wave itself, not quite. Good guess. Not. I mean, if we were to say energy, then yeah, we would say it's a scalar quantity. Let's think, whoa, what's energy? Okay. Let's start simple. Yeah.
Is heat a vector quantity?
No, it's not. That's energy. Same thing as light. Light and those are all chapter 9 stuff. We'll get there. Man, you guys want to just keep going to the next chapter. Okay, we'll do it in 3. Oh, no, we'll do it in 6. Oh, we'll do it in 7. It's like, now 9. Ooh, you guys. Why'd you skip 8? Just kidding. Okay. So, any other ideas, or should I give you something to build off of? Oh, yeah. Let's give you something to build off of, right? So, let's talk about one we talked about today. Force. Force is a vector quantity. Why? Who can tell me why? Go ahead, Caleb.
Because it has a certain amount of force being pressed against things, and it also goes certain directions.
Yeah, does everybody understand this? Does anybody not understand that? Don't be afraid to not understand, but just say so that we can help you. Caleb, come on up. I'll show you. That's what I see. Most of them are pointing towards you. Okay. So if I push on this table, maybe I'm pushing with 5 newtons of force. So Newton is the SI unit of force, right? Not pound is also a unit of force, but we only us Americans use that. So in science, we'll just deal with newtons. Okay, if I push with 5 newtons of force, 5 newtons is the magnitude. And what else do I need for a force? What way am I pushing it? I'm pushing it east. So 5 newtons east. Whenever you guys give me an answer for a vector quantity amount, you better include what? A direction. You have to, otherwise it's half wrong. Are you with me? Did you write that down? That's something good to know. Okay? So if you ever use a vector or give an answer for a vector quantity, you better include both the magnitude and the direction. Okay, so a force is an example of a vector quantity. Can anybody give me another example of a vector quantity? Oh, that's all we talked about today, so not really. Should I give you a scalar quantity? Area. If I find the area of this table, it's 2 by 12, 6 by, so let's just say 12. It's 12. Is that good enough? No. 12 square feet. Oh, is that good enough? Should we say 12 square feet north? No, that wouldn't make any sense, would it? Okay. Sometimes it would make sense if it's a scalar quantity, but only if there's like a pair. And we'll talk about that in a minute. Okay, so area. Who can tell me another example of either one of those, scalar or vector quantities? Go ahead, Kate. Time is what? A scalar quantity. Hey, what time is it? Well, it's about 3 o'clock east. No, that's dumb, right?
What about time zones?
Time zones?
No, I mean,
But would you still say a direction? No, you just say Mountain Standard. You wouldn't say Mountain Standard North, right?
when you're asking for direction,
Then you ask for directions. Go ahead. What?
Friction is vector.
Yeah, it is a vector quantity because friction is a force. And forces are vector quantities. Yeah, you're right. Anything else? Just tell us. Yeah. Volume is also a scalar quantity. What about temperature? No, it's not. But good. Yeah, a lot of people think they're the same. They're not. It's a measure of warmth, which is not heat. What? What is it? Scalar or vector? Scalar. Temperature. Anything else? There's one that we use every day that we didn't talk about. Speed. What's speed? A vector or scalar?
Scalar.
Hey man, how?
Oh wait, speed.
Oh man, dude, how fast can your car go? Yeah, I could go like 70 miles an hour north, dude. Could we say 70 miles an hour north? We could. But only if you're a nerd, right? We have a special name for speed with the direction. Anybody know what it's called? Velocity. And speed is a scalar quantity. Does that make sense? So those guys could be saying, oh, you probably could do 70 miles an hour north. But if we do, we call it velocity. So what's the definition of velocity? Speed with a direction. That's it. Are we good? Anything else? Talked about another one today. What am I doing right now? What am I doing? I am slowing down, aren't I? What do we call that? There's another name. Acceleration. Friction causes acceleration. Okay, acceleration, what is that? Scalar quantity or vector quantity? Vector quantity. I can if I accelerate, what way was I accelerating? What way am I accelerating? That way. I'm accelerating that way. If I continue to accelerate that way, watch what happens. Ready? I'm accelerating that way and I continue to accelerate that way, watch. And now I'm speeding up this way. That's the direction of the acceleration. Isn't that what we think about when we say, put on the accelerator, dude? We say go faster, right? No, we don't talk that way, Mr. O'Brien. Right? Okay. Are we good? So acceleration is a vector quantity. That's probably a good enough list for now, yeah? There's more, and as we talk about them, we'll get there, and we'll... All right. One more thing about a vector. So vectors. We draw them like this. Why? Is there a difference between those two vectors? And one of them is longer, right? So what does the length represent?
Distance.
It could be in a displacement vector. We'll get there. But what does the length represent? This is a vector, and what's a vector? Something that measures both magnitude and direction. So what's the length of the vector represent? Magnitude. Yeah, that's right. And what's the arrowhead represent? Direction. Are we good? So this one just means it has a bigger magnitude. Same direction, bigger magnitude. If it was a force vector, it'd be a bigger push, right? Or a bigger pull. Are we good?
Yeah.
All right, let's talk about net force. We already did a little bit during the reading quiz. Do you guys have any questions so far? Okay, Donica, no questions? Okay, great. Thank you. So let's see. Net force. What's the definition of net force again, everybody? Or the sum You could say combination, that's still right? The sum of all forces on an object. Of all forces acting on an object. What do I mean when I say acting? They're not real. They're just pretending like there's something different. Oh, not that kind. It's just a push or pull, right? It's acting on it. It's either pushing on it or pulling on it. The sum of all forces acting on an object. Okay? So if it's the sum, we have to be able to know how to add these, yeah? So let's try to make sense of Let's try to make sense of how we add these. Y'all with me? Thank you. So if I push on this in the eastward direction, let's say with 10 newtons of force, or 5 newtons of force, am I changing the object's state of motion? Am I? This is at rest, and it's staying at rest. Did I change its state of motion? No. So how can we change an object's state of motion? By applying a force, right? Applying a what? A net force. When I say, so that's the real answer. You guys write that down? That is on the test. That is a test question. The test question will say, how can you change an object's state of motion? And the answer is by applying a net force. Or actually, it might not say that. It might say what causes an object's state of motion to change. And you would say, not a force, but a net force. Good? What causes an object's motion to change, right? Right now, this table's motion is what? It's not moving, it's at rest. Can we change its state of motion? Yeah, by, sorry, did that hurt? Sorry. Okay, so we just changed it. Was there a net force on it that time? Yeah. But if I push with 5 newtons, there's no net force on it. That means the net force equals 0. You get that no means 0?
Yes.
Okay. Because I don't want wording to change your idea on something. Or say, yeah, that's not what it says. It says no net force. So if there's no net force, then it's not in equilibrium. But that's what equilibrium means. 0 net force or no net force. Net force equals 0. That's what it means. You with me? Okay, I just gave you the answer to a quiz or test question that a lot of people get wrong because of wording. Do we understand this? Okay, so if I push with 5, now let's go back to adding vectors. So if they're in the same direction, so for example, if I push on this table with 5 newtons, and I can't get it to move, and Rhea comes over here and she says, hey, let me help you. And so she pushes on it with 5 newtons of force, and then it starts moving. Well, let's say it doesn't start to move, but let's say we push it. 5 newtons, 5 newtons. How much force is acting on this now?
10.
What's the net force? 10, right? Kind of. We'll get there, okay? Because there's another force that we're not talking about. What is it? Friction, right? Okay. But if there's 0 friction, I push on it with 5, and Rhea pushes on it with 5, then what's the net force acting on this object? 10. You with me? So when we're in the same direction, we add them. If they're in the opposite direction, what do? Does that make sense in your mind? Because if I'm pushing this way and Ray says, I don't want this to move. So she pushes it back, 5 newtons and 5 newtons the opposite direction. What's going to happen to this table? Nothing's going to happen. It's going to stay at rest, right? So 5 in the positive direction, 5 in the opposite direction, which is negative. So negative 5 and positive 5 make 0. So we subtract them. Are we good? All right. We'll keep it simple today, and next time we'll talk a little bit more about, there's one more way to add vectors. And if you've been high in math, you probably know, but maybe you don't recognize it. All right. Let's do an example. Okay, let's say we have, so this right here that I'm drawing represents something that will not move. It's like stuck, kind of like the ground outside is stuck, right? Or the ceiling, you can hang something from a ceiling and it's not going to move the ceiling, right? So there's the ceiling or the roof or whatever. And let's hang some scaffolding. You guys know what scaffolding is? It's like a plank that workers can be on there and they're going to paint this building that's high up, yeah? So we got the scaffolding. And let's say we got the painter right here. And we got his paint bucket over here. And there is a scale right here and a scale right here. And let's say this scale reads 1,000 newtons. Is that a lot of newtons? Well, I don't know. How much do you weigh? Do you guys know how much you weigh in newtons? Let's see. You know, in pounds. So take your weight in pounds and divide it by 2. This is a simple way, not a complete way. Divided by 2. So if I weigh 200 pounds, divided by 2, that's 100, right? And then times by 10. That's 1,000. I weigh 1,000 newtons. Yeah, and that's a lot, Mr. O'Brien. You're a big fatso. Yeah, okay, I need to work on that. Okay, so let's say that's 1,000. And this painter guy, he's a lot more fit than I am. He weighs 500 newtons. And the board weighs 200 newtons. And the can of paint weighs, let's say, 100 newtons. And let's say there's another guy over here. We'll make him a blue guy. And he weighs 800 newtons. Can anybody tell me what that scale is going to read?
1,000.
No!
I can.
Okay, figure it out. Are you sure? Are you sure?
Yeah.
Don't tell me. Don't tell me. I want everybody to be thinking. That's why I yelled. Because I don't want you to be selfish. I want you to let everybody have a chance of thinking about this. What would this scale on the left, don't tell me, what would it read? We will be good. We will be good. Oh, good. Oh, we're all massive. We all have mass. Just kidding. I don't think I would necessarily call her massive. You guys, she's not. Okay. Does everybody have this? Is everybody like, what? How are we supposed to do that? Anybody feeling like, what? How are we supposed to do that? Raise your hand if you're thinking, what? How are we supposed to do that? Okay, so just 2 of you are thinking, how are we supposed to do that? So I can ask anybody else and you'll tell me? Yeah? I'm not hearing a no, so I'm just going to call on one of you. And that'll be fine. Are we proud, ladies and gentlemen? We don't even want to tell me that you don't get it. That's like, oh my gosh, people are going to think I'm stupid because I don't get this stuff. Ladies and gentlemen, this is brand new for all of us. Some of us might get it quicker than others, and that's okay. You just got to tell me, how's it going? Then we don't have to have this conversation. Do you get that? We can already move on. Okay, so talk to me. That way I don't embarrass you on accident. I'm not trying to embarrass you. It shouldn't embarrass you, but okay, I know how we are. We just want to be right on everything. But we're not. Okay, let's move on. Here we go. Can anybody tell me the net force on this entire system? Can anybody tell me the net force on this entire system? Raise your hand if you can tell me. Bridger. Is it 2,600 newtons? No, it is not. Thank you for participating. Okay? Is it what? 1,600 newtons. No, it is not. But thank you for participating. Jeremiah.
400.
Is it 400? I'm not talking about what this reads. I'm talking about our whole system. What's the net force of our whole system? I don't know if it's 400 or not. It's not. But thank you for participating. Mary, you love her. No, but thank you for participating. Landon.
2,000?
It is not, but thank you for participating. I'm getting the same people over and over again, so maybe we should just talk about it real quick. Caleb? What is it?
1,000?
No, thank you for participating. Okay, let's talk about it. Because we're just guessing. Let's make sense of this. How can we change the object state of motion? With applying a net force, right? Is this system's motion changing? No, it is not. It's all at rest. So what is the net force on this system? 0. Are we good? Question. What questions do we have? Jeremiah.
How do you know it's 0?
Because when an object is in equilibrium, the net force is 0. We're kind of jumping the gun. We kind of talked about it for our reading quiz, didn't we?
How do you know it's not moving that?
If it were moving, that would be dangerous.
Could be telling me a little bit on one side.
It would still be dangerous. We're the safety kids. See this? I said this is meaning it won't break, it won't fall down. This is holding it, and there's nothing that's going to move it. Nothing. Yeah, you can do this and get it to sway, but they're not. They're painting. They're painting. Are we good?
Yeah.
All right. So the net force is 0. That means if we add up all of these forces, we're going to get what? 0. I added them up and I got 2,000, Mr. O'Brien. You're nuts, right? But did we add this one? Okay. All right. So now see if you can figure out what this is. Don't tell me. See if you can figure it out. Does that give you a better idea or no? Try it. Don't tell me. I'll ask in a minute. I want everybody to try to figure this out. Because if you're not learning. And if you get it wrong, no big deal, we're still learning. So just a sec. Give everybody a chance. Do you have a question or an answer? Okay, what's up? Yeah, so the can of paint is 100 newtons. Kind of wrote that kind of weird, but okay. Who wants more time? We all got an answer then? Okay, I don't know what the answer is yet. Let me figure it out. Caleb,
600?
is it 600 newtons? What do you guys think? I'm seeing one nod, yes. Two of them, yes. Three, yes. Yeah, 600 newtons. Should we go through it and show how to figure out this? Okay. Well, okay. So we know how to add vectors, right? Which one should we add first? All these guys. Why all these guys? They're in the same direction. If they're in the same direction, how do we add them? We pluff them, right? We just add them up. So we add those together, and what do we get? 700, 800 plus 800 is 1,600 newtons going down. How much force do we have to have going up if the net force is 0? 1,600 newtons. There's 1,000 right there, so this side has to be 600. Do you get that? Question.
Took the guys away and not the board with it.
What's that?
I just took the guys away and not the board with it. Because everything else was on the one other side.
You just split it in half and added them up?
Took the guys away and then I did half of the boards away.
Yeah, you did split it in half. That is what you did.
That is what I did.
The way I did it is the way you should do it. You might have got lucky. So you cut it right in half. Whoops. So you cut it, let's just make sure. So we cut it right in half. And you said there's 100 on this side, 500 on this side. There's 100 on this side, this 100, and this 800. There's 1,000. That means that you got lucky. Yeah, it won't always work that way. Do you understand how to add vectors? Yeah, if they're in the same direction, you add them together, just plus, right? If they're in opposite directions, what do? Subtract. So we have 1,600 going down. That's why we added them. And we're going to subtract this because it's going up. We're left with 600. And we know we have to go to 0 because it's in equilibrium. So this has to be 600 to go to 0. You with me? Questions? Good? All right. Should we try some more on your own? Yeah, you guys picked up a worksheet, right? If you didn't, they're over there. Did you take that quiz yet? Reading quiz? Okay, come see me another time. Make it up. You got to take the test still, right? Okay. Let me know when you're ready. Okay, ladies and gents, this paper right here, I want you to work on number 1. Before you can answer number 1, what do you got to do? Read it. Should we read it together?
No.
So you can read it then?
Yeah.
Okay, read it.
Did it.
We will talk about it. We definitely will.
And that one.
We definitely will. I want you to use your thinker real quick.
I did.
Keep using it. We'll get there, I promise.
And this one.
Yeah, we'll get there. So let me tell you how this works. It starts out simple as it can get. And then as it goes down, it gets harder and harder and harder and harder. That's the hardest one. So I don't want to just start there. Good? But keep thinking about it. There you go. Yeah.
What's 12 plus 20? He wants to know.
Okay, there's a calculator over here. If you don't know how to do that in your head, use a calculator. I am not your calculator.
It's 32, right? It's 22.
It's 32.
It's 32.
Do you have a question? On. Why?
Because there's no, it's not moving or anything, so the force is 0.
There you go. So you got a tension force and a weight force, right? There's two forces, and this one's going up and this one's going down. And she's at rest, right? Tells us that, right? The net force is 0 on all these because they're not accelerating. Yeah. That's it. Did we do the front side? Yeah, ladies and gents, start on the front side. Side where it says 2-1 on the top.
Can I get help with number 4?
Number 4's a little.
We're not on number 4. Did you do number 1?
Yep, and 2 and 3.
Here's number 1.
Yeah, I'm done with that.
It's not right. Try it again.
What?
Some of it might be, but not all of it.
What is this?
I think I was right.
This is just a corner. She's hanging off of a cliff with her hand, with one hand on the cliff and one hand on this ring.
So is it saying half her weight is on this?
It's not saying anything. It's just drawing a
Why would it be
picture.
75? There's 3 different ones.
So,
What's 300 divided by 3?
is half her weight on here and half her weight on here? What makes you think that? Because this is right smack in the middle. Half is on this, half is on this. Does it look just like this, right smack in the middle? Half is on this, half is on this. Okay. That's a good way to think about it. So is it that?
Is this correct now?
We're not trying to trick you. We're trying to make it simple. What do you think? Is it going to be 300 right here?
I don't think so.
What if you had two bathroom scales and you put one foot on one foot on the other, and you stood right in the middle? What would each of them read? Half of it, right? Yeah, that's it.
They probably are 100, but we just don't know. Maybe?
Not all of them are right.
Can you just tell us?
You can. Okay, ladies and gents. Do we have any questions on number 1? That's all I wanted you to work on. But okay.
The last one.
The very last one and the second to the third to the last one. Okay. So first of all, the first one. Did everybody get 300 newtons?
Yes.
Any questions on the first one? You ladies with me?
Yeah.
We all good with the first one?
Yeah.
The second one, we're hanging on a bar with 2 ropes, right?
Yeah.
Since she's right smack in the middle, how much is on each side? 150, half and half, right? We good? What if you have 3? Oh, a third on each side. 100, 100, 100. Are we good? And then the next one, she's like this. We got 2 scales. I'm just going to draw her like that. Are they 150 apiece?
No.
Well, look, draw this, ladies and gents. How much is hanging right there? All of it. All of it. How much is hanging right there? All of it. Do you get that?
Yeah.
It's the same tension rope, same tension, same force. 300. They both read 300 newtons. Are you with me?
Yes.
The common mistake people make, that's the way to think about it. And the next one, how much is hanging off of that scale? I'm talking about the one where she's hanging off like this, right? Half her weight is on the ledge, half her weight is on the scale. You with me?
Yep.
Does anybody have a question?
What?
Okay. Do number 6 like we did this one. Do number 6 like we did that one.
Hit 300 or other. I said that at first. But then a certain child said,
So is this 300?
He also said it was 22 and not 32. You can believe him?
No.
Just
Is this
kidding.
right?
Don't bully.
Oh, sorry.
He's just teasing.
So is this 300 right there?
Yes, because if you draw it like this, how much is hanging off of that? All of it. Hey, ladies and gentlemen, if we had, let me draw this real quick. I said, let me draw this real quick. How much would this scale read? 300, all overweight, right? Because all overweight's hanging off of that point. You with me?
yep,
What if we put the scale right here? Then what would it read?
300.
300. What would we read right here?
300.
300. It's the same rope. Just like this one, guys. It's the same rope. It's 300, tension of 300 newtons in the whole rope. Okay, are we good?
Yes.
All right. Okay, give me tension in 5, 4, 3, 2, 1. Let's give you some definitions here. Mechanical equilibrium. There's a lot of different types of equilibrium. Equilibrium means it's balanced. It also means what? Sum of forces is 0. Net force equals 0. Okay, so same thing with mechanical equilibrium. Mechanical is more so net force equals 0. Can you have thermal equilibrium? Yeah, let's say you get a pan of hot water and you decide, I guess we're going to go out to eat. So you're just going to make spaghetti or something. And you get it all boiled up and then he's, okay, just shut it off. We're going to go out to eat, right? Yeah, you guys ever do this? Okay, so you do that. You put the pan, you just leave it in the kitchen, turn it off. What happens to that water?
It stays hot for a while.
It does stay hot for a while. But what happens to that water? It cools. It cools until it reaches what? The room temperature. Then when it reaches room temperature, it's in a state of thermal equilibrium. So you get that? It's kind of the same idea, but a little bit different. Okay, so mechanical equilibrium states that no physical changes occur. But let's just sum it up. It means the net force equals what, Mallory? Yeah, net force equals 0 newtons. What else does it mean? It means that the state of motion is constant. Constant, let's see. Does it mean it has to be at rest? No, it doesn't. It means its state of motion is constant. How else can you have a state of motion that's constant if you're not at rest? You're moving.
It doesn't lose speed.
Same speed, almost. Same speed, same velocity, which includes what? Direction. Speed with the direction. Yeah, we just barely learned that word today, so no big deal. So if I'm going the same speed, same direction, I'm at constant velocity, constant state of motion. You with me? And if I'm in a constant state of motion, whether it's at rest or at constant velocity, then I'm in a state of equilibrium. Are we good? These three go together. If you have one, you have all. If you're in a state of equilibrium, your net force is 0, and your motion is constant velocity. Could that constant velocity be 0? Yeah, if your velocity is 0 and it doesn't change, that means you're at rest. Yeah? So at rest means constant velocity equals 0, doesn't it? You with me? All right. And we have a special name for equilibrium at rest. Anybody know what it is? What is it? Somebody said something. What's equilibrium at rest? There's equilibrium in motion and equilibrium at rest. Not quite. Here it is. Where else have you heard static? Static electricity. Guess what that means? Electricity at rest. When you get in, you're under the cover, and in the night, and you start seeing sparks, right? You ever do this?
Yeah.
Because your sheet has static electricity. Once you start seeing the sparks, it is no longer static. It'll shock you, right? It's moving. But just sitting there, and you see the little furry things of your blanket pop up, right? Yeah, it's static electricity. Are we good? Electricity at rest. That's what static means, at rest. So this is equilibrium at rest. Are we good? Okay, ladies and gents, let's work on this worksheet for the remainder of the time. We have 10 minutes left. Should we collect this at the end so we don't have homework on this? But you will have some homework. Your homework is to read chapter 2.3 to 2.4. Did you write that down in your planner?
Yeah.
Read chapter 2.3 to 2.4.
And take notes.
And take notes. Get ready for a quiz, right?
On Thursday?
Next time, yeah. So next time is Thursday, yes. Is this a B Friday or a Friday? Was it B Friday last time? A Friday last time? But hold on. Wasn't it B last time?
It's because of Labor Day. They're making it Labor Day.
Okay, good. I hope so, because my A Day would get behind. Yeah. What?
I just need you to check me out and see what I did wrong.
How do you know you did anything wrong?
I don't know. I'm pretty sure I did wrong on the fourth one.
Okay. So, fill in the total reading scale. The total weight is that 1,200 or 800 or 1,600? 1,200. Okay. If he weighs what? 600. And if he's right smack in the middle, then this has to be 600, right? Okay, that's right. So that means everything here. So if he weighs 600, what is everything else? What does this board weigh?
Wait.
Wait a second. 0.
No, the board doesn't weigh 0. The board weighs
He weighs
600. Then the board weighs 600.
Board weighs 600. Yeah, it does.
No.
Yeah, it has to.
Yes.
It has
You
to.
weirdo.
Right?
Yeah, because
So this is 1,200.
Yeah.
And this is 12. Yeah, that's it.
Okay,
You
what
got
about
it.
these ones?
You tell me. Are they right?
I think they are.
I want you to know for sure.
Okay.
Did you add them?
I did.
Okay. Are you right?
Okay.
Yeah,
I'm
these
right.
are right. That
Okay,
one's
so
right.
how much weight is pulling down? 1,200? How much weight is pulling up? 1,200? Should be 1,200, because that's 1,200, right?
Yep.
Yeah.
What's pulling down? 1,200? Oh, what does this have to be? Oh, my gosh. Does he weigh 600?
He weighs 1,000.
Oh, he weighs 1,000. Oh, yeah. So 1,200. So since he's in the middle, it's the same on both sides, right?
Yep.
Yeah, there you go. 13 ton, 19 ton. Is that equal to 12 ton? Is that 12?
That is 12.
Oh, that's just that guy.
Yeah.
And this is 20, so that's 32.
Yeah, not
Oh.
22.
I was having that.
Okay, so we got that then?
Yeah.
Yeah.
Is this equal to 32?
Yes.
Okay. Yeah. Does this all work that way? See how I figured that out?
This
and
one-
checked it?
I need
No,
help
you
on
do
this
it.
one.
I think I did.
What is the tension?
Yeah.
Could you help me?
In just a second. Did you try it? Did you try it?
Well, I don't know how to do it. I did what I
You do it the exact same way as the rest of them.
We do 4 on the
need help
board.
with the tension, though.
This one?
Yeah. Can we do
Hold on, ladies and gentlemen. You guys want to do 4? Yes. Did we try it yet? No. Okay, that's homework.
Wait, are you guys tried it? 500 and 500 on
Yeah, what is tension?
Did you read number 4?
Yeah, we did.
It gives you information.
What does normal mean? What is that? We already did this. No, like,
Oh, the normal force?
is it like how it normally is? Like that?
Huh.
Normal force is a support force that
Oh,
would measure 90
she
degrees
she wrote it
So,
down in her notes. Isn't
1,000?
that nice?
Wait, so that means it's perpendicular, so that means...
I don't know. Is the net force this way? What's the net force this way on this object?
It's 1,000. Oh.
Is it?
I don't know.
Hey, ladies and gents, listen up. Everybody, I'm going to give you a hint. I'm not going to give you the answer. I'm going to give you a hint. You ready? Listen. If I move in this way, does gravity affect how I move this way? Does it?
No.
No, it doesn't. It does not. It affects how I move this way. Does me pushing affect how I move this way? Up and down? No. Because I'm pushing this way. Right? Are you with me?
Yes.
That's what I'm saying is directions. You got a T2 circle rating.
So this is the top.
They're different. Keep directions. I mean, one direction is opposite. You do those together. And up and down you do together. But you don't do those together. You with me? We add x's and y in math? No, we don't. They're different.
What would the normal be? What's normal?
It's the same. Anyway, I did that. All this
Hey, ladies and gentlemen, we have like 3 minutes left. If number 4 is not right, then I don't want you to turn it in.
I'm turning it on.
Time to clean up.
Do you want this?
No, ladies and gentlemen, if you turn this in today and the bottom one's not right, you don't get credit. But if you want to turn it in, there it is. Put it down. That's the question. We'll find out. I talked about it.
So we will get credit for all of it, except for this one we get really good.
If you have this one right, I'll give you credit. So if anybody wants to turn it in, it's right here. If you don't, turn it in on canvas.
Hey, do you want to have a bet?
You have to push that one and pull that one all at the same time. It's screwed in there. Let's not hang out at the door, gentlemen.